Hello and welcome back to educator.com and welcome back to biochemistry. So today we're going to start talking about disaccharides, putting two monosaccharides together in something that's called a glycosidic bond. So let's go ahead and get started. All right, so let's see, how can we do this? So a disac is exactly what it sounds like. CCH, I always forget how to write that. Disac is made of two monosacs joined covalently. Actually, you know what? Let me just joined by a covalent bond called an O-glycosidic bond. Very, very, very important bond in biochemistry. So it is the hydroxy group of one sugar has reacted with the anomeric carbon of the other sugar. Anomeric carbon of the other sugar. Now, when we say the hydroxyl group of one sugar, the truth is it can actually be any of the hydroxyl groups, but in general it's going to be specific hydroxy groups that are going to react with the anomeric carbon of the other sugar. So again, you'll see from the bond which particular hydroxy is going to react, but it actually can be any one of them. Okay, so let's just go ahead and do examples of these. We'll just go through several examples to get a sense of how to put the structure together, how the bonds are drawn, the perspective drawings that we're going to be using, and how we're going to name them systematically. So that's what's important. So let's do examples. Of disacs and how to name them systematically. How to name them. Okay, so let's go ahead and start with a particular disaccharide. Let's start with alpha-D-glucose and connect it to beta-D-glucose in something called a 1,4 connection. Okay, so let's go ahead and draw out our alpha-D-glucose. Again, always proceed systematically. Start with your basic unit. So alpha-D-glucose, we're looking at this thing right here. So, God, I really love the blue. I think it's my favorite. Okay. CH2OH. So this is alpha-D-glucose. Alpha-D-glucose. And now we're going to be joining it with, so I'll go ahead and put a little plus sign here. We're going to be joining it with beta-D-glucose. So let me draw out the beta-D-glucose first. Here. So beta is going to be up here, but everything else is the same because we are talking about glucose. So CH2O4. Okay, so now when we put this and this together, let me go ahead and do a red. I'm going to number my carbons. So this is number 1, number 2, number 3, number 4, number 5. And again, 1, 2, 3, 4, 5. I'll go ahead and put 6 too. That's not a problem. And again, standard position, oxygen is in the back right, the anomeric carbon is on the right. That's the reducing end of the sugar. This over here on the left is the non-reducing end of the sugar. In this particular case, let me go ahead and write. So this is beta-D-glucose. So again, there's a bunch of hydroxys here that can actually react with this anomeric carbon. In this particular case, we're going to form a 1,4 connection. So the anomeric carbon, the number 1 carbon, is going to be connected to the number 4 carbon, and here's the reaction that's going to take place. What's going to go away, this is a condensation reaction. In other words, the elements of water are going to be taken away from this. The elements of water that we're going to be taking away, right there. This hydroxy on the anomeric carbon is going to go away, and this hydrogen on the connected to the oxygen on the number 4 is going to go away. So the oxygen that's going to end up being the go-between between this unit and this unit actually belongs to this carbon, the number 4 carbon. So what you end up with is the following. So let me go ahead and draw a couple of arrows, one this way and this way. And if we go this way, we're actually losing water. If we come this way, we're actually adding water. So this is a hydrolysis. When you hydrolyze a disaccharide, you get 2 monosaccharides. When you condense 2 monosaccharides, you're getting the disaccharide. Okay, and this is how it's going to look. I'll do this one in red. Boom, boom, boom. Boom, boom. Okay, I'll go like this and up like that. And then I've got that, 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 that. Okay, this is the beta, and now I'll go ahead and fill in my rest. This is up. This is down. This is CH2OH. This is down. This is up. This is involved in the bond. This is CH2OH. Okay, this particular sugar is called maltose. Maltose, this is the common name. So in the sugar maltose, what has happened is that an alpha-D glucose has reacted with a beta-D glucose. The anomeric carbon has reacted with the number 4, with the hydroxy on the number 4 carbon to create this right here. So this right here, this is your O-glycoside bond. Okay? That's your O-glycoside. O because the O is involved. And notice, down, down. That's why it's drawn this way. This is how we actually represent the arrangement in space, but we keep this particular perspective so that we see how the molecules, how the individual units are arranged. This is how we do a disaccharide. Okay, the name for this is alpha D, because it's a polymer, glucosyl, the first 1, 4, D, glucose. Alpha D glucosyl, that's the first monomer, arranged in a 1,4 pattern. 1 on the left connected to the number 4 carbon on the right. That's where this 1,4 in parentheses means, and a little arrow going from the 1 to the 4. We go from left to right. D-glucose. Okay? Actually, I should actually write this as, because we've actually specified the stereochemistry on this particular monomer. It's the B. This is beta D glucose. Now there's a slightly longer name, but we're actually going to be dealing with a shorter name. I'm going to write the longer name, but then we're going to exclusively start dealing with the shorter name. So this is also called, and I'm not going to draw out the structure again, you can just flip back, alpha D glucopyranosyl, remember pyranose 6, glucose pyranosyl. It's a little redundant, but you will see it. Pyranosyl 1,4 beta D glucopyranose. Now obviously you can't use something like this. So here is the shortened version. All of the sugars, just like the amino acids, they have 3-letter shortcuts for them. So like ALA is alanine. Well, in this particular case, glucose is GLC. And there's a list in your book of the three-letter shorthand notation for all of the individual sugars: galactose, glucose, ribose, deoxyribose, whatever it happens to be. So in this particular case, the name is going to be written this way: GLC for glucose. We write the configuration at the carbons that are attached by the O glycoside bond. The two carbons that are involved in the bond, we give their configurations. Alpha 1, to 4. The fourth carbon, we don't alpha beta because the alpha beta designation is only for the anomeric carbon. So alpha 1, 4, beta GLC, also written as GLC alpha 1, 4 GLC. Often the monomer on the right, the fact of the matter is, well, I'll tell you in just a second why it is that I wrote beta here and not there. So let me go ahead and tell you what's going on. So this does not mention the beta explicitly on the second monosac because something called mutarotation it often switches the configuration. So even though we know that, we use the beta version of the second monosaccharide, the fact of the matter is the alpha and beta forms, they actually often switch. So the stereochemistry on the reducing end of the sugar, the one that has the free anomeric carbon, it's often unspecified. So sometimes you don't necessarily have to put the beta there. It's not a problem unless specifically they want you to. So in this particular case, we put together an alpha glucose with a beta glucose, and what we ended up with is GLC glucose alpha 1 configuration at the anomeric carbon connected to the number 4 carbon, the hydroxy on the number 4 carbon, and the other disaccharide was a glucose. That's all that happens. It switches the alpha beta configurations. So again, either one of these is fine. If you want to specifically write the beta, that's fine. If not, you're not going to have any points taken away. Okay. Now, again, as I said, if the anomeric carbon on the second monosac, in other words, the one on the right on the monosac, is free, like it was with maltose, then this is called the reducing end of the sugar, because now you have a disaccharide which happens to be a reducing sugar. Iron 3+ or copper 2+ will still oxidize that end, so it's available to be oxidized. It isn't always the case. In a minute you'll see an example of something that is not a reducing sugar, a disaccharide, but this one, because the anomeric carbon, that hydroxy was not involved in the O glycoside bond, it's still free, it is a reducing sugar. So it is called the reducing end. And again, we have a reducing sugar. So let me read that again. So if the anomeric carbon on the second monosaccharide is free, then this is called the reducing end. And again, we have a reducing sugar. And of course, the other end, the one on the left, the one that cannot be oxidized, that's the non-reducing end. Okay, so maltose, what we just did, is a reducing sugar. Maltose is a reducing sugar. Okay, now, as we said, any of the OH groups on the second monosac can react with the anomeric carbon of the first monosac, can react with the anomeric carbon of the first monosac. Okay, excuse me. Even the hydroxy on the anomeric monosac, even the OH on the anomeric C. Let's look at an example. Okay, now let's go ahead and look at, so let's look at the sugar trehalose. Let's look at the Disaccharides trehalose. Okay, so let's see what we have here. Now, trehalose, we're going to have an alpha-D glucose and an alpha-D glucose that are going to be connected by their anomeric carbons. So let's go ahead and draw the alpha-D glucose. So we have this alpha is right there. That's there. That's there. That's there. This is CH2OH. So this is alpha D, and I'll just put GLC for glucose. Now we are going to connect it to another alpha D glucose. Down, up, down. Okay. So this time, they're connected. The number 1 carbon is connected to the number 1 carbon. How are we going to show that? Okay, so, but now, the OH on the, no. The OH on the number 1 carbon of the second sugar, number 1 carbon, the anomeric carbon of the second sugar is going to react with the anomeric carbon of the first. Sugar reacts with the number 1 carbon of the first sugar. Okay, how are we going to deal with this and how are we going to represent it? We're going to do this in 3 different ways. Well, let's see. Let's just write. How do we deal with that? How do we represent this? Schematically, how do we actually show the bond? How do we represent this? Okay. Here's how we do it. We either flip or spin the second sugar so that the ends that are going to be reacting are close to each other. When we do that, we're going to have to change the arrangement of the second sugar. In other words, now it's no longer going to have the conventional representation of the oxygen being on the back right. So let's go ahead and, so how do we deal with this? Well, we flip or spin the second monosac for a new arrangement on the page. For a new arrangement on the page. Okay, so let's go ahead and do the first one. I'm going to do both. I'm going to do a flip first. I'm going to do a spin first because you're going to probably see them both. My guess is more often than not in most biochemistry books you're actually going to see it flipped, but you'll see the spin version too. This is really, really, really important. There's lots of carbons and oxygens and hydrogens floating around here. Do not go through these structures quickly. Make sure you understand, make sure you pay very close attention to where each individual atom is, particularly that oxygen, because that's what's going to give away the structure and what it is that's going on. Okay, because all of these things actually look alike. The only thing that actually tells you what's different is the arrangement of this particular oxygen in the second monosaccharide. If it happens to be back, if it happens to be forward, that tells you which carbons have reacted. Okay, so let's go ahead and deal with a flip. So we're going to actually end up flipping this one, and the reason we're flipping it, in other words, I'm saying flip it this way, because you want this carbon to be over on this side because you want it to be close to the carbon that it's going to be reacting. We've already told you that trihalose is connected, the anomeric carbon, carbon number 1 and carbon number 1 are the ones that are connected via the glycosidic bond. So we need a way to represent this on paper, so we want to flip this so that this bond over here, we don't just want to draw this line connecting them. Okay, so let's draw this one again. Let's do it in blue. So we've got this, 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 that, 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 and this is alpha. So this is going to be here. Okay, so we've got CH2OH. Now, what I'm going to do is I'm going to, wait, where am I? Okay, yes. So now I'm going to flip this. Okay, when I flip this, I'm just flipping it like this. Everything that's on the right goes to the left. Everything that's on the top goes to the bottom. Things move around. So I'm going to redraw it like this. One, boom. Okay, I've taken it and I flipped it. Now, what used to be, let me number these. One, oops, I want to do these in red. 1, 2, 3, 4, 5, 6. Now what you have is, I've flipped it, so now it's 1, 2, 3, 4, 5. And let me actually finish off the structure. And this is, so let me do the structures here. When I flip this, this is on the bottom, it goes over to the right, and now it's up here. This O has moved over here. This C has moved over here, this 5 carbon. But now this is up. Now this is down. CH2OH. Okay? The number 2 carbon, it's down. So this is going to be up. Number 3 carbon, this is up. So it's going to be down. Number 4 carbon is down. So now it's going to be up. This is the flipped arrangement. So now, okay, does that make sense? Notice where each group is. 1, 2, 3, 4, 5. I've flipped it. It's not a mirror image, okay? It's not a mirror image. I've actually flipped it. Everything is reversed, not mirror-wise, but this way. That's what's going on. What I needed to do was I needed to bring my number 1 carbon to put it in close proximity with the number 1 carbon of my first monosaccharide. So now this thing is going to react with this thing. Okay, 1, 1. So the elements of water that are going to disappear is the hydroxy there, the H here. This oxygen is going to be attached to that carbon. When I put those together, this is the arrangement that's going to take place. What I end up with is the following. This is the same. We haven't done anything to the first monosaccharide. That's CH2OH. But this one, things are a little different. We have flipped this other one. So this does not look the same. You might think it does, but it does not. And it's very, very important that you realize where the oxygen is, okay? Here the oxygen is on the top right, back. Let me draw the perspective. Okay, here the oxygen is in the back left. Here the CH2OH is on the upper left above the ring. Here it's on the back left, but the CH2OH is below the ring, okay? This 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I flipped it so that I could put these two carbons, the ones that are reacting, in close proximity so that I can represent this glycosidic bond in this fashion. Okay? When this is an alpha, so the hydroxy is below the ring. This is also an alpha. In conventional position, the hydroxy is below the ring, but because I flipped it, I now have the hydroxy above the ring at that carbon. That's why I draw it this way. So this is alpha D glucosyl 1 double arrow 1, double arrow when you're connecting anomeric carbons. Alpha D glucose. The shorthand notation, GLC for the first monosaccharide. Alpha 1 configuration. That carbon, the number 1 carbon, it is an alpha configuration that's involved in the glycosidic bond. The other one is also the number 1 carbon of the second monosaccharide in alpha configuration. That's the other carbon involved in the glycosidic bond. And just go ahead and put that. This is what you want to write. GLC, alpha 1 double arrow, alpha 1 GLC. This is trehalose. Okay? Now you notice the anomeric carbon, the reducing end of one carbon, reacted with the reducing end of the other. This end over here, it is not available for oxidation. Okay? It's not available for oxidation, so this particular sugar doesn't have a reducing end. Therefore, this is a non-reducing sugar. Trehalose is a non-reducing sugar. This changes the chemistry entirely. They behave in completely different ways. Notice, if you were to just look at this really, really quickly without even sort of thinking about it, it would look almost exactly the same as the sugar that we just did, which was maltose. I mean, yeah, you might notice that this particular thing is different, but you might think to yourself, oh, maybe they just drew it differently, that's all. No, there's nothing random here. Everything is drawn with a specific purpose. What you would notice on maltose is that on both monosaccharides, the oxygen is in the back right. Here, the first monosac is on the back right. The second monosac, the oxygen is on the back left. We've specifically drawn it like this. This is what's important. So you really, really have to pay very close, detailed attention to these particular structures. Okay. I'm going to go ahead and do the spin version of this real quickly. So again, this is just something that you may see. So I'm going to take my alpha D glucose. So let me draw that under standard. So alpha D glucose, hydroxide, hydroxide, hydroxide there, hydroxide here, and CH2OH. Now instead of flipping that second monosaccharide, I'm going to go ahead and spin it. So when I spin it, I end up with the following. Let me see. Yeah. Okay. When I spin it, it means I'm not flipping it, I'm just spinning it 180 degrees. I'm rotating it this way. Flipping means like that. Spinning or rotating means like this. So here's what it ends up looking like. Boom, boom. Now the oxygen is in the front left. Okay, so basically just follow all of these things and just go to the opposite pole. This goes here. This goes here. This goes here. That's all you're doing. So it ends up like this. That OH goes there. This ends up coming CH2OH. This is down, so it's going to stay down. This is up, it's going to stay up, except now it's going to be in the back. And I think I've covered everything. So what you've got is 1, 2, 3, 4, 5, 6. Now what you have is 1, 2, 3, 4, 5, 6. Now notice in this particular case with the spin arrangement, now my oxygen is down below the ring. So when I draw my trihalo structure, here is what my structure is going to look like. This stays the same. That, and that. That's going to go like that. And here, oxygen is there. So OH, 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 CO2OH, and now we have OH, 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 and we have CH2OH. Okay, this is again glucose, alpha 1, in parentheses, double arrow, because now double arrow, I'm connecting the anomeric carbon with the anomeric carbon. Each one has an alpha configuration, and they are both glucose monomers. Notice, this is the exact same thing as this. Notice here, the glycosidic bond is represented this way, below, above. The oxygen on the second monosaccharide is on the back left, but this was based on the flip. Here, I've decided to spin it, and now the glycosidic bond is represented this way. This is the same molecule. This is not a different molecule. It's just that the second monosaccharide is arranged in a different way. The first monosaccharide is exactly the same. This is why it's really, really important to be able to distinguish. Watch for where this oxygen is. Watch for where the number 1, number 2, number 3, and number 4 carbons are. Here it's 1, 2, 3, 4, 5, 6. Here it's 1, 2, 3, 4, 5, 6. This is the same molecule, different arrangements in space. Okay, so you've seen the spin, you've seen the flip. I'm actually not going to go ahead and show you the third version. I don't think your teacher actually wants you to do that anyway. So, okay. Now, let's see. So trehalose, again, is a non-reducing sugar because there is no anomeric carbon that might open up to release a free aldehyde that can be oxidized. So completely changes the biochemistry. Okay. Let's go ahead and do an example. Well, I mean, we've done a couple of examples, but let's just do sort of a free example. Okay, sucrose, which is table sugar, is GLC, alpha 1, beta 2, FRU. Okay, so sucrose is a disaccharide, and it is made up of a glucose unit and a fructose monomer. So glucose is a hexose, it's a 6-membered sugar. Fructose, remember, is a 5-membered ring sugar. The connection between the two, the glycoside bond that connects them, connects the anomeric carbon, which is alpha, and the number 2 carbon, which is beta configuration on the fructose. So let's go ahead and draw out the structure. That's our assignment. This is what we want to do. So in this particular case, we haven't given you a structure. What we've done is give you the name in shortened form, and we want you to draw the structure. Draw the structure. Very, very typical question on an exam. Okay. In this particular case, so, well, let me just go ahead and draw the, should I go ahead and, well, that's fine. So in this particular case, I'm joining the anomeric carbon of both. So again, I'm going to have to bring the carbons in close proximity. So I'm going to have to flip or spin the second monosaccharide. I'm going to choose the flip version. So let me go ahead and draw out my, so I choose to flip the second monosaccharide. Second monosac. Okay, and again, when you see an alpha or a beta on this second carbon here, this second sugar, that's what's going to tell you that you're probably going to have to do some spinning or flipping. If there was just a number here like 4 or 5 or 3 or something like that, then you can just leave them alone and just connect the carbons. Okay, so let's go ahead and draw out our alpha glucose. So that's going to be like this. Alpha, which means the hydroxy is down here. And this is there. And this is there. And this is CH2OH. Okay, now flip the beta. Let me see, 2. I'm actually going to go through the process of putting this particular fructose together. So I'm going to start the process this way. So I'm going to do this in blue, just so you see, again, a little bit of a review on how it is that we actually create this particular ringed sugar. So fructose, again, is a 6-membered ring. So we have 1, 2, 3, 4, 5, 6. That's up. It's going to be down. Yes. Okay, so except this time, see, this is H2OH, so this is a ketone, this is a ketose, so the number 2 carbon actually has the carbonyl. So here, OH, so I'm drawing out the linear form, 1, 2, 3, 4, 5, oops, I forgot. This is OH, and this is CH2OH. So this is the linear form. So I'm going to go ahead and take this linear form and draw it in such a way in order to create my ring. So let's see, I've got C carbonyl. This is CH2OH here. This is C. This is C. That's C. And then I have my OH. And I have my CH2OH here. So this is in free form that I've taken. I've rotated. I've brought the other thing around. Now, 1, 2, 3, 4, 5. That's right. So I'm going to end up attacking that right there. And what I'm going to end up creating is my beta fructose. So my fructose is going to look like this. And I have that. So beta, that means, so this is the number 1 carbon, right? Number 1 carbon, number 2 carbon. So CH2OH. Let me go ahead and number these. This is 1, this is 2, this is 3, this is 4, and this is 5. And I'll do number 6 in just a minute. Let me go ahead and put all of my substituents on here. Oops. As you can see, things get very, very, very involved. So let me go ahead and put my hydroxy there. Let me put my hydroxy there. Let me put my CH2OH over here. And I have my beta configuration. So this is my, write these out, this is my alpha glucose. And this is going to be my beta fructose. So I started with my fructose linear form. I created my regular beta fructose. This is the standard conventional arrangement. I'm going to be reacting this with this. Alpha 1, beta 2. So I'm actually going to be connecting this carbon with this carbon, which means that I'm going to have to flip this so that I can bring this carbon in close proximity to this carbon. Now, when I flip this, here's what it's going to look like. I'm going to do that in red. So the flipped fructose, I'm going to flip it. Well, the arrangement that way actually stays the same, but of course the substituents look different. So now what I have is, this is down, so it's going to be up. So this is going to be CH2OH. This is up, it's going to be down. This is CH2OH. This is down, this is up, so it's going to be down over here. And this is going to be up. This OH is up over here on the right. It's going to flip around this way, so it's going to end up being down here. So it almost looks the same, except the carbons are numbered differently now. So now we have our number 1 carbon, number 2, number 3, number 4, number 5, and number 6. So that, oops, go ahead and do that. So now I'm going to connect. This is our first sugar. This is our flipped fructose. I'm going to connect that carbon with this carbon, the number 2 carbon. And in case, so you notice this hydroxy is down, and over here, this hydroxy is down below the ring. So my final fructose structure, I'm sorry, my final sucrose structure is going to look like this. I've got this. Let me make this kind of big. Okay, I've got 1, 2, there, there, there. Let me go ahead and draw my glycosidic bond. 1, 2, 3, 4, 5. This is an oxygen, and now I can put my substituents in. Hydroxy down, hydroxy up, hydroxy down. CH2OH. Now I've got a hydroxy down here. I've got a hydroxy up there. I've got a CH2OH here. And I've got a CH2OH. Actually, let me draw it to the left because there's plenty of room on the left. CH2OH. And there we go. Now I have my alpha 1 configuration, alpha 1 carbon on my glucose. This is my beta 2. You can write B2, 2 beta. It doesn't matter the order. That, you know, as long as the alpha 1 is on the left of the arrow. And okay, so we have GLC, alpha 1, double arrow, beta 2, FRU. This is sucrose. This is table sugar. And you notice there is no anomeric carbon that's available. This is a non-reducing sugar. The 2 anomeric carbons are connected by an O-glycosidic bond. It's arranged this way. This is not the standard conventional arrangement. I've had to flip this fructose monomer in order to bring this carbon in close proximity with this carbon. This is the process that you go through. Again, glucose, glycosidic bond. Glucose is connected to fructose. The glycosidic bond is the alpha 1, number 1 carbon alpha configuration connected to the number 2 carbon beta configuration. That's it. We'll do more of these. Don't worry about that. We'll do plenty of these because it's very, very important that you be able to go back and forth, that you see a structure, be able to name it, that you be given a name, and be able to draw out a structure for it. Okay, thank you so much for joining us here at educator.com. We'll see you next time. Bye-bye.